This is SpaceTime, Series 21, Episode 72. Coming up on SpaceTime, new clues about Earth's greatest mass extinction event, the most detailed map yet of nearby galactic cosmic X-ray sources, and new clues about supernovae. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims that halogens released during the Siberian Traps eruption may have been one of the driving forces behind the world's greatest mass extinction event. The findings, reported in the journal Nature Geoscience, suggest that halogens effectively destroyed planet Earth's ozone layer, making what was already a disastrous situation even more deadly. The end Permian mass extinction event occurred around 250 million years ago, killing some 90% of all life on Earth. The event, also known as the Great Dying and the Permian-Triassic mass extinction, occurred when the biggest volcanic eruption in the last 500 million years ripped open what is now Siberia. This massive basaltic lava flow lasted more than 2 million years. It was triggered by a mantle plume, which rose until it impacted against the bottom of the Earth's crust, triggering volcanic eruptions through the Siberian Craton. The eruptions generated a volcanic winter, causing temperatures to initially plummet and then soar, while at the same time pumping the atmosphere full of poisonous gases. The magma sea generated by this event, now known as the Siberian Flood basalts, covers an area which today is about 7 million square kilometres, with some 4 million cubic kilometres of basaltic rock. And that same mantle plume is still alive and active today, under the Atlantic Ocean, generating the Iceland hotspot. The study's lead author, Michael Broadley from the Centre for Petrographic and Geochemical Research in France, says the scale of the Permian mass extinction was so incredible, scientists have often wondered what made the Siberian flood basalt so much more deadly than other similar eruptions. The authors examined samples of mantle xenoliths, rock sections dragged up by passing magma which eventually erupted onto the surface during volcanic explosions. These mantle xenoliths originate in the lithosphere, the region of the Earth encompassing the deep crust and upper mantle, and so they're able to provide scientists with a detailed sample of the composition of the surrounding lithosphere. The authors found that before the Siberian flood basalts took place, the Siberian lithosphere was heavily loaded with chlorine, bromine and iodine, all chemical elements from the halogen group. However, these elements seem to have disappeared after the volcanic eruptions. Broadley and colleagues conclude that the large reservoir of halogens that was stored in the Siberian lithosphere was sent up into Earth's atmosphere during the volcanic explosion, effectively destroying the ozone layer present at the time and further contributing to the mass extinction event. You're listening to Space Time. I'm Stuart Gary. Astronomers have developed the most detailed map ever of cosmic ray sources in two of the Milky Way's nearest galactic neighbours. The findings, reported in the monthly notices of the Royal Astronomical Society, show regions of stellar formation and the echoes of stellar death in both the large and small Magellanic Clouds. Cosmic rays are highly energetic particles, mostly atomic nuclei but also electrons, travelling through space at highly relativistic speeds. Of the atomic nuclei, about 90% are simple protons, in other words hydrogen nuclei. A further 9% are alpha particles, identical to helium nuclei, while the remaining 1% are mostly HCE ions, the nuclei of heavier elements. There's also a small fraction of cosmic rays composed of stable particles of antimatter, such as positrons and antiprotons. Though some cosmic rays are produced by the Sun, the most powerful are generated far beyond our solar system by things like supernovae during the death of massive stars, and by the active galactic nuclei of black holes. Researchers use the Murchison Wide Field Array radio telescope in outback Western Australia to examine the large and small Magellanic Clouds, a pair of dwarf galaxies visible from the southern skies. Both galaxies were mapped in unprecedented detail as they orbit around the Milky Way. By observing the sky at very low frequencies, astronomers were able to detect cosmic rays and hot gases in the two galaxies, identifying patches where new stars are born and remnants of stellar explosions can be found. One of the study's authors, Professor Lister Stavelli-Smith from the International Centre for Radio Astronomy Research, says the number of cosmic rays that are produced depends on the rate of the formation of massive stars millions of years ago. It's the first time galaxies have been mapped in such detail at such low radio frequencies. By observing the Magellanic Clouds at these low frequencies, between 76 and 227 MHz, the authors were able to estimate the number of new stars being formed in these galaxies. They found the rate of star formation in the Large Magellanic Cloud is roughly equivalent to one new star with the mass of our Sun being produced every 10 years, while the rate of star formation in the Small Magellanic Cloud is roughly equivalent to one new solar mass star every 40 years. Two areas specifically targeted in the observations were 30 Doradus, an exceptional region of star formation in the Large Magellanic Cloud that's far brighter than any star formation region in the Milky Way, and Supernova 1987A, the brightest nearby supernova observed since the invention of the telescope.
Yes, we've been using the Murchison Wide Field Array, which is a relatively new radio telescope that's based here in Western Australia. And more or less for the first time, we've been able to make a very high resolution, that is a very detailed map of both clouds at these very low radio frequencies.
And you've been looking specifically at cosmic rays that are coming from supernovae.
Yeah, most of the radio emission that we see at low frequencies is what we call synchrotron radiation.
That's got something to do with electrons, hasn't it?
That's right, electrons or protons, but mainly electrons. You know, we have a synchrotron accelerator in Victoria, of course, yeah. But this is a cosmic accelerator, much higher energies and much more distant. So what we believe happens is there exist very highly charged particles, which we call cosmic rays. These are very highly energetic particles, and when they interact with magnetic fields, they generate this special form of low-frequency radio emission, and that enables us basically to see the cosmic rays, or rather see a combination of the cosmic rays interacting with the magnetic fields at very large distances from us.
What does that tell us about the galaxies?
So our understanding is that these cosmic rays, now these are very highly relativistic particles, are actually generated during the explosions of massive stars, that is, during supernovae. So when stars whose initial mass is about 10 times that of our own sun, when they explode, when they go supernova, there is unleashed a huge amount of energy, and some of that energy goes into, under a mechanism that we don't fully understand, to be honest, goes into accelerating electrons and protons to very, very high energies. So what, in fact, these cosmic rays are, what they tell us is they tell us about star formation and stellar death, and particularly the most massive stars that we know of.
And by looking at these cosmic rays, you've been able to work out what the star formation rates in both the large and small Magellanic Clouds are likely to be. Here in our own Milky Way, it's about one solar mass of new stars every Earth year. What about the LMC and the SMC?
Yeah, indeed, they're much smaller galaxies, but relative to the mass, they're actually quite strong star-forming galaxies. The SMC is only about a 40th of a solar mass per year, but given the size of the galaxy, that's quite a high star formation rate. And that star formation rate reflects the birth rate of the most massive stars, which we believe is reflecting the sort of underlying birth rate of stars which are more like our sun.
So there's a sort of a set ratio, I guess, well, a hypothesized ratio between the amount of big stars that are being made, high mass stars, compared to the amount of normal dwarf stars like the sun.
Yeah, that's right, and that's a subject of extreme contention at the moment. It's not something we can resolve with our observations, but the so-called, we call it the initial mass function. Technically, it's quite contentious, and a lot of debate about that using observations and theory.
The large and small Magellanic Clouds are two, I think it's now confirmed that they are satellite galaxies of the Milky Way, as opposed to simply just very close passers-by. They're constantly interacting with the Milky Way, aren't they? Stellar streams, gravitationally, that sort of thing.
Yeah, there's a lot of contention about that, despite the fact they're our nearest luminous gas-rich neighbours, nearest to the Milky Way, that is, because it's a fairly complex three-body interaction. The small cloud, the large cloud, and the Milky Way. And because we don't fully understand the dynamics, although the new Gaia satellite is helping a lot in that regard, it's still not absolutely clear whether the Magellanic clouds have been orbiting the Milky Way for some time, or whether even they're just on their first passage, their first infall. So the field is still, our understanding has still got some way to go.
This is obviously showing you some of the new potential of the wide field array.
Yes, particularly the radio quiet location we have at the Murchison Radio Astronomy Observatory has allowed observations at these very low frequencies. It's allowed us to see this special low frequency synchron radiation to measure star formation rates without having to resort to observations of dust or without having light impeded by the presence of dust. But by comparing with existing higher frequency maps, we've also been able to pick out sites of what we call thermal radiation, sites which are associated with current star formation rather than past star formation. And we can do that just by looking at the relative strength of the emission at different radio frequencies. And the power of our radio telescopes in Australia is we can do this. We can use the low frequencies at the Murchison Radio Astronomy Observatory with the MWA. We can use the intermediate frequency band at ASCAP, the Australian SK Pathfinder, which is more or less at a similar location. And in the past, we've also been able to use the Australia Telescope Compact Array in New South Wales, and still can, to measure the high-frequency radiation.
How does Parkes fit into all this? What sort of frequencies does it look at?
So Parkes looks across a very broad range of frequencies, but the power of Parkes is that it's got a very large collecting area, and in fact, Parkes is essential in looking at objects like the Magellanic clouds because they're so big. So Parkes gives us a much better view of the diffuse radiation from those clouds, and it also enables us to look for pulsars. So pulsars are usually created, pulsars are spinning neutron stars created in the aftermath of the explosion of massive stars. And in fact, since you mention it, we've just been allocated some observing time at Parkes to look for the pulsar, which is predicted to be present at the center of supernova 1987A, which was a massive star which you might remember exploded 30 or so years ago.
And there's been a lot of controversy over that because for a long time it wasn't known whether it was a neutron star or possibly a black hole that was formed as a result of that explosion.
That's right. Well, we know absolutely there was a neutron star formed because neutrinos were detected by neutrino detectors at the time of the explosion. That's how neutrons are formed when protons, electrons come together. They turn into neutron and emit neutrinos. So we know a neutron star was formed, but it is nevertheless possible, as you suggest, that there was later fallback, and that fallback could have sort of sent it over the edge into a black hole. Theorists believe, as far as I understand, theorists now believe that's probably not the case in this particular instance, but that's one of the reasons we have to look. If there's a neutron star, we hopefully we'll see it either in the X-rays or in the radio at some stage once the debris has sufficiently cleared. But no one has yet done that. But from time to time we will be trying. There's about 19 neutrinos detected, not many, and this was in a couple of neutrino detectors around the world.
Yeah, they arrived before the first photons did.
Exactly.
That's Professor Lister Stavelli-Smith from the International Centre for Radio Astronomy Research. And this is SpaceTime. I'm Stuart Gary. Astronomers have discovered a previously undetected flash which occurs just before the death of a star in a core collapse supernova explosion. The findings reported in the journal Nature Astronomy aren't predicted by current models, and so changes science's understanding of supernovae and the final stages of stellar evolution. Supernovae are among the brightest events in the universe, created by the death of a star, in the process generating enough power to briefly outshine an entire galaxy. The newly detected flash was seen in stars known as red supergiants. The flash occurs about a week or so before the supernova event reaches its climax. It occurs as the expanding gas of the supernova collides with material surrounding the doomed star. The study's lead author, Francisco Foster from the University of Chile, says the presence of this material makes it possible to extract part of the enormous energy produced during the explosion and turn that brilliance into light which can be detected. The discovery was made by scanning the skies using DCAM on the 4-metre Victor Blanco telescope at the National Science Foundation's Cerro Tololo Aura Observatory in Chile. Forster and colleagues examined 26 supernovae coming from red giants. Their goal was to study the shock breakout, a brief flash of light preceding the main supernova explosion. The problem is they couldn't find any signs of this phenomenon. On the other hand, 24 of the 26 supernovae they studied appeared to brighten faster than expected. In order to solve the mystery, the authors simulated 518 models of supernova brightness variations and then compared them to the observational results. They found that models containing a layer of circumstellar matter, about 10% the mass of the Sun, surrounding the supernova, provided the best match for their observations. It seems this circumstellar material hides the shock breakout, trapping the light. And the subsequent collision between the supernova ejector and the circumstellar matter creates a strong shock wave that produces extra light, causing it to brighten more quickly. The findings suggest that near the end of its life, some mechanism in the doomed star's interior must be causing it to shed mass, which then forms a layer surrounding the star. Right now, the authors don't have a clear idea as to the mechanism which could be causing this mass loss. The discovery was made possible because the explosions were observed in real time in their initial stages. The findings will enable astronomers to collect more supernova samples, giving them a better understanding of these extreme events. It'll also be important in revealing the supernova explosion mechanism and the origins of the diversity of supernovae. I'm Stuart Gary. This is SpaceTime. One of the many legacies of NASA's Cassini mission has been a surprising feature emerging out of Saturn's northern pole. The feature, detected as the ringed world was nearing its northern summertime, was a warming high-altitude vortex with a hexagonal shape, akin to the famous hexagon seen deeper down in Saturn's northern clouds. The discovery, found in the reams of information sent back to Earth before Cassini's demise, suggests that the lower altitude hexagon may influence what's happening higher up, and that the whole thing could in fact be a towering structure spanning hundreds of kilometres in height. When Cassini arrived at the Saturnian system in 2004, the southern hemisphere was enjoying summertime, while the northern hemisphere was in the midst of winter. The NASA spacecraft spied a broad, warm, high-altitude vortex at Saturn's southern pole, but none at the planet's northern pole. But a new long-term study has now spotted the first glimpses of a northern polar vortex forming high in the atmosphere as Saturn's northern hemisphere approaches summertime. This warm vortex sits hundreds of kilometres above the clouds in the Saturnian stratosphere. And it's revealed some unexpected surprises. The study's lead author Lee Fletcher from the University of Leicester says the edges of this newly found vortex appear to be hexagonal, precisely matching the famous and bizarre hexagonal cloud pattern seen deeper down in Saturn's atmosphere. Scientists always expected to see a vortex of some kind as Saturn's northern pole grew warmer. However, Fletcher says its shape was still surprising. Either a hexagon has spawned spontaneously and identically at two different altitudes, one lower in the clouds and the other higher in the stratosphere, or the hexagon is in fact a towering structure spanning a vertical range of several hundred kilometres. Saturn's cloud levels host the majority of the planet's weather, including the pre-existing northern polar hexagon. This feature was first discovered by NASA's Voyager spacecraft in the 1980s, and it's been studied in detail for decades. It's a long-lasting wave, potentially tied to Saturn's rotation, a type of phenomenon also seen on Earth in structures such as the polar jet stream. Its properties were revealed in detail by Cassini, which observed it in multiple wavelengths from ultraviolet to infrared, using the spacecraft's array of instruments including its composite infrared spectrometer. However, at the start of the mission, this instrument couldn't peer further up into the northern stratosphere. That's because temperatures there are around minus 158 degrees Celsius, some 20 degrees too cold for reliable infrared observations, leaving these higher altitude regions relatively unexplored for many years. And of course you've got to remember that one Saturnian year spans roughly 30 Earth years, so from our point of view, winters on Saturn are really long. And Saturn only began to emerge from the depths of its northern winter in 2009 and gradually warmed up as the northern hemisphere approached summertime. Then a strange process at play in Saturn's atmosphere sped up this warming. As air sank at the North Pole, the upper hexagon warmed increasingly quickly, and the transport of air downwards made the abundance of several minor molecules more concentrated. It was this increased temperature which allowed Fletcher and colleagues to finally study their polar vortex in infrared light. They were able to use the composite infrared spectrometer to explore the northern stratosphere for the first time from 2014 onwards, 10 years after Cassini's arrival at Saturn. As the polar vortex became more and more visible, the authors noticed that it had hexagonal edges, and they realized that they were seeing the pre-existing hexagon at much higher altitudes than previously thought. What all this indicates is that Saturn's two poles behave very differently. Scientists have never seen a hexagon at the South Pole, either at the cloud tops or above when it was observed early in Cassini's mission during the southern summer. The northern vortex is also nowhere near as mature as the southern vortex, as it's cooler and displays different dynamics from its southern counterpart. This could mean there's a fundamental asymmetry between Saturn's poles which scientists are yet to understand. Or it could mean that the northern polar vortex was still developing during Cassini's last observations, and kept doing so after Cassini's mission ended in September 2017. The presence of a hexagon in Saturn's northern stratosphere, hundreds of kilometres above the clouds, suggests there's much more going on and consequently much more to learn about the dynamics at play in the gas giant's atmosphere. The problem is, a single towering hexagonal structure which stretches high up through the atmosphere would be unlikely given that wind conditions change considerably with altitude. However, by investigating the atmospheric properties in the northern region, Fletcher and colleagues also determined that waves like the hexagon should be unable to propagate upwards. They should remain trapped at the cloud tops as previously thought. One way wave information could leak upwards is through a process called evanescence, where the strength of the wave decays with altitude but is still just strong enough to persist up into the stratosphere. Understanding how and why Saturn's northern polar vortex has assumed a hexagonal shape will shed fresh light on the phenomenon deeper down in the atmosphere and how that can influence the environment higher up. I'm Stuart Gary. You're listening to SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study claims being optimistic about stuff is actually good for your heart. The findings, reported in the Journal of the American College of Cardiology, are based on numerous separate studies all showing that optimism and a feeling of purpose in life were associated with a lower risk of heart disease and stroke. They also found that optimistic patients were less likely to be smokers and more likely to exercise and eat healthy. The authors say intervention programs are available to strengthen psychological well-being. Activities like yoga and Tai Chi were shown to improve the health of heart failure patients. A new study warns the already endangered Australian fur seal population is shrinking. The findings, reported in the journal PLOS ONE, are based on a census of the annual Australian fur seal pup population. It found the first reduction since species-wide protection was implemented in 1975. Meanwhile, in a separate study of Australia's fragile ecosystem, world-renowned ecologist John Wolanarski from the Charles Darwin University has released a new book on the extinction of the Christmas Island pipistrelle. The book is both an obituary and an inquest into the extinction of this tiny Australian bat species, whose last individual died in 2009. Yet another Australian species now extinct. E-commerce stores worldwide have been infected with new payment skimming malware. The malicious software, called magnetocore.net, intercepts customer payments and sends it on to cybercriminals. The malware was able to infect websites using Magneto shopping cart software by successfully guessing the password used by the website's Magneto admin panel. Infected websites record all keystrokes from customers, capturing usernames, passwords, credit card information, and personal details. Online store owners are being advised to analyze back-end logs and look for any unusual administrator logins. And if you're an online shopper, double-check your accounts for any unauthorized transactions. Well, hot on the heels of last month's discovery of 3,200-year-old cheese in an Egyptian tomb, scientists have now found evidence of cheese making in Eastern Europe around 7,200 years ago. A report in the journal PLOS ONE claims archaeologists have found fatty acids on vessels unearthed in Croatian archaeological sites which were occupied between 6,000 and 4,800 BCE. and that suggests people were making cheese about 2,000 years earlier than previously thought. Researchers think cheese making may have helped farming communities expand into colder, more northern latitudes. Apple says neither its iPhones nor any third-party apps on them listen in without user consent. The tech giant gave assurances to the US Congress after the House Energy and Commerce Committee asked the company if its devices were invading users' privacy. That came following concerns raised about Siri's wake-up commands. Apple told lawmakers iPhones do not record audio while listening for a Siri command, and Siri doesn't share spoken words. Apple says it requires users to explicitly approve microphone access, and apps display a clear signal when they are listening. With more details, we're joined by Alex Zaharov-Reutt from IT Wire.
Well, that's without consent. I mean, Apple does things with your consent. Apple is listening and getting data from you if you agree to allow that to happen. And it's made very clear, and Apple is very strict on the way that it uses your data. But, of course, it is using your data, but, again, only with your consent. On the other hand, you have Google that has just been announced by an Associated Press report that testers were noticing that even when you explicitly turned off location history, Google and various apps were still capturing that history. And Google says, you can switch off web and history activity in your Google account, and you can switch things off. But you've got the Google side of the fence that sort of wants to take as much data as it can, whether really you give permission or not, and then use that in ways to enhance its services. Whereas Apple is more constrained; it has to get your permission, and even then, there's all sorts of things that it won't do, whereas Google will do them. And so in some ways, Apple has been a little bit behind in some of its efforts with artificial intelligence and Siri, whereas Google has just sort of been able to use your data as it has decided it wanted to, because you sort of ticked the box that said yes, but didn't really know what you were saying yes to. And look, the government is asking, well, who's listening? Well, Apple has said, well, we're not listening unless you give permission. But of course, if you give permission, then they're listening, but they're not using that against you or using that to identify you specifically. They talk about having that data being anonymized and randomized. And so, look, this battle will continue, and it's this touch-and-go area of how to advance technology but still keep privacy in check. And ultimately, we should strive to be the generation that ensures privacy is passed down to our future generations as something to be sacred, as opposed to being something that we gave up and forgot about just so we can get a free app.
And that report by Alex Zaharov-Reutt from IT Wire. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favorite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.